Hi, and welcome to this Calculus 1 video on graphing derivatives, and we will also look at one rationalizing example where we use the definition of the derivative using the limit process, and we go through rationalizing. So we have already gone through a few of these in a previous video where we were given an original function and we went through how to come up with that function's derivatives graph. And we talked about the derivative being the slope of the tangent line at any point. So as you look along any curve, you're trying to look what is the slope of the tangent line at each point along the curve, and that's what you're plotting. You can generalize it by talking about whether that slope is negative or positive, large or small, things of that nature. And the most specific points that need to be on your graph, of course, are those turning points. So we did see that, for example, in graph C, where those two turning points are where my slope of my tangent line is horizontal, or in other words, the slope of that tangent line was 0. So right now I'm going to talk you through this example, which is our 1D, and why this derivative is what it is. So if we look at this 1D, the blue is the original function, okay? And if I look at all of these slopes of these tangent lines for, let's just say, the right-hand side, the yellow highlighted area that I just looked at there, so all of these slopes of these tangent lines are negative. And further, they are negative large, right? That's a negative, pretty big number over there. They're steep slopes, okay? And then eventually it's looking like my slopes level off. It's still negative, it's still decreasing, but it's a really, really small slope, something that might be approaching 0. So what I did for the red graph, or to get my derivative graph, is here's large negative slopes going to more flat or smaller negative slopes as I progress through the x values. And again, this derivative graph is leveling off at 0 because that's what my slopes of my tangent lines to my original function look like they're doing. Sometimes you need to hear these comments twice as well, so there's nothing wrong with pausing this video and rewinding it just to hear a piece of it again. So if I look at the other side of this graph here, so this blue function, okay, I just highlighted that in yellow as well. So to the left of the x-axis, what we're looking at here is these slopes of these tangent lines are also negative the whole way through. So at any point along that curve, I can draw the slope of the tangent line, and it's a negative sloping tangent line. And so I can approximate here, they're approaching 0 again. They're negative really, really small. But, you know, as x gets larger and closer to that y-axis, these are negative really big. They're negative very steep slopes, okay? And so that's what the red indicates. So what you'll actually notice is the derivative of these. Let me see if I can take off all this mess here so you can see the red derivative a little bit better. So the red derivative is actually going to almost look like a mirror image or a reflection of each other, just in the third and fourth quadrants. So that would be the derivative of the original function. One important note is that you had a vertical asymptote in your original function. So if I look at my original function in blue, it appears that there is no x value for x equaling 0. Well, if that's the case, then I should not have an x equals 0 on my derivative either, because again, a derivative is a description of the original. So if the original function doesn't exist, I certainly wouldn't want to describe it there. All right, and then the last one of these, again, you're going to get better at reading these graphs probably without values on them. In fact, I think it's less chaotic or less busy, maybe easier to understand. So try to maybe pause the video and walk yourself through the scenario of, if the blue was my original function, why is the red the f prime function? Well, the first thing that you should have probably talked about to yourself is that this turning point up here, I have a horizontal tangent line at that x value, which will correspond to an x-intercept on my derivative. Because again, that's where my derivative equals 0. That's where my slope of my tangent line equals 0 at those highlighted marks. Okay, so then what? Well, all of the blue section here that I will highlight have positive slopes, but they're really small. They get a little bit bigger here in the middle, and then they get really flat again. So small, bigger, smaller. So that's what you'll notice my red does. It's very small. It's actually even under here. You can't really even see it. And then it gets a little bit bigger in terms of positive slopes in terms of their value. And then they get smaller again. So this might be a slope of like 1, this might be a slope of 2, etc. And then the exact opposite occurring on the other side. These are all negative slopes, whereas those were all positive slopes. So my entire derivative graph should be below the x-axis. But again, the same thing is happening in terms of smaller, bigger in the middle, smaller, right? And so these y values are small, a little bit bigger, smaller, approaching 0. So let's see if we can do something which I think is really interesting here. Let's take 3 graphs, and you are going to identify which is the original, which is the first derivative, and which is the second derivative. So I'm going to also actually write over here on the side f of x equals which graph, f prime of x equals which graph, and f double prime of x equals which graph. Now, what we also are going to ask you to do is to explain why are you choosing what you're choosing. So please write down some of the terminology as we say it and what makes sense to you and how you can relay that back. So there is really no right or wrong here. You pick a graph to start with. So let's just say B jumps out at me. I don't know, it doesn't really matter. I can start with any of them. So if I take a look at B, and B, I'll highlight it first just so, because I don't know why the red sort of jumped out at me, I guess. So if that is my graph that I want to see, okay, what's going on with B? Does B have a derivative, first of all? So could B, for example, be the original or be the first derivative? Because then its derivative would be here. If B does not have a derivative graph on here, then I know B must be the second derivative. All right, so let's look at what B could be. Well, again, I'm going to look at turning points first, and I'm going to look at positive and negative behavior after that. So I see a turning point approximately right here. And so if I follow that down, oh look, there's approximately an x-intercept. Again, that turning point is where you have a horizontal tangent or a slope of your tangent line of 0. So that's where your derivative graph should be crossing the x-axis. Now before you go rushing and say, oh good, B's derivative is C, well, let's make sure that the positive and negative behavior matches up as well. So we are positive sloping before we get to that first turning point. So my derivative graph should be above the x-axis, and they are. They are also, I don't know, decently big, and then as you move up, they get smaller, approaching 0. So that's the trend that that's taking so far. Then my other turning point on B occurs probably right about here. And if I follow that up, yep, that is in fact about where my x-intercept is of that same C graph. And I would keep kind of looking through B here. So all of this section right here, B has decreasing or negative sloping tangent lines, right? A decreasing function has negative sloping tangent lines, which means that its derivative from that x value to that x value should be below the x-axis. And that's exactly what was happening with that graph. Okay, so I know so far B's derivative is in fact C. But what I don't know is where does a fit along here? So a could either be c's derivative or a could be the original function. So I need to figure out which is which. So you have a choice. You can start with c and see if that derivative is a, or you could start with a and see if that derivative is b. Doesn't matter. So let's just say I start with an a and see if a could be the original function. Well, if a has a turning point right here and right here, its derivative should be 0 at those same x values. And if I follow this down, it appears that that is c. So I think, okay, wait a minute. Maybe I got these behaviors wrong. So let's take a look at this section right here. So in between those two zeros, right, because it looks like everything matches up. So maybe a's derivative is c, and that's not really a possibility the way I have it written out right here. I said b's derivative was c. So if a's derivative is that c or blue graph still, look at this section that I sort of squiggly lined in between these two turning points. Those should have positive slopes, right? Those are positive derivative values. Well, in between those x values, take a look at the graph for c. They are all negative y values. The graph is below the x-axis. So a's derivative is not c or b, which means a's derivative is not on there, so the order should be bca. The last thing I think you might want to do is just double check that, in fact, c's derivative is a. So if you look at c, here's a turning point for c, for example. Well, that could be a or b. But I probably have a turning point coming up somewhere over here. Same thing. So I would need to look at positive and negative behavior at that point. So I have positive sloping tangent lines in this section right here. And so my derivative graph should be above, from that x value on, should be above the x-axis, which is a and not b. So I know a has to be c's derivative. You can start with any graph you want. So for example, on the next graph, I'm going to start with graph B for a very important reason. I'm going to write the same thing, f of x equals, so which one is the original, which one is the first derivative, and which one is the second derivative. And by all means, this does absolutely take practice. Okay, so I'm going to start with B, and I have a reason why. So I'm going to start with B. And B is my green curve in this case. I'm just going to highlight it in green. Oops, even a little bit more here. Okay, so green, or B, only has one turning point, right? And it's right about there. And if we follow that up, we find that we're kind of in a world of hurt pretty quickly because no other graph crosses the x-axis there. Okay? Well, let's see. C crosses the x-axis, right? C crosses the x-axis over there, and A crosses the x-axis in two places. I have nothing telling me that B is turning around or that it will have that behavior while I will have a horizontal tangent line at those values. So I don't think there is a derivative for B graphed here. Here's the other reason why. From this point on, if you look at B's slopes of their tangent lines, they're all positive. So from this x value on, your derivative graph of B should be above the x-axis completely. It should never go back below the x-axis, and both A and C do. So I know that B does not have a derivative on my graphs here. There is no choice for that. Okay, so B has to be that second derivative. So now you have choices. It can either be CAB or it could be ACB. So you just need to determine, is C the derivative of A or is A the derivative of C? So it doesn't matter. We'll just start with A because it's first in the alphabet. So let's take a look at A. I'll highlight it here so it's maybe a little bit easier to see. Okay, A has a turning point, so that's where I would probably start. So A has a turning point about right here maybe. And if I follow that up, that's looking pretty close to this value. So maybe A's derivative is C. Let's make sure the behavior matches. So from this x value to the left, so left behavior of that x value, all of those derivatives or slopes of the tangent line should be negative, right? This is decreasing to the left here. Okay, so that means that if truly A's derivative is C, that means then that C should be below the x-axis the whole time. So look, it's below, 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 below. Yep, that worked. And then it's above. Now also, it's pretty steep throughout the whole time in terms of slopes, so it makes sense that it's pretty far below the x-axis. So I know A's derivative is C, and then you could also go through the same process and verify that C's derivative is in fact B. And again, you would want to write this out in words so that you can explain your thoughts. Okay, here will be our last question where we are asked to find the derivative using the definition of the derivative, which I have listed below, and also state the domain of the original and of the derivative. So let's go ahead and start with the domain of this function. So here's my function, and we should know that we have to have a 0 or greater value underneath my square root, meaning I cannot take the square root of negative values and come out real. So I want to force 1 minus 3x to be greater than or equal to 0, and I will solve that inequality. So I'll subtract 1 from both sides. Divide by negative 3. Now watch your inequality when you divide by negative 3 because it will switch that sign around. A lot of us use a number line to help us with our interval notation with domains. So here's my 1/3. It is all values less than or equal to 1/3, so there will be a bracket and it's heading to the left. So in terms of domain of f of x of the original function, it would be negative infinity to 1/3, and there's a bracket on 1/3. And I'm going to go ahead and highlight this because I'll keep it because we'll reference it later. Okay, now I was asked to find the derivative using the definition of the derivative, so I wrote that out for us. Remember, the f prime of x was the limit as h approaches 0. Don't forget your limit or you forgot your calculus. Of f of x plus h minus f of x all over h. So let's find that f of x plus h so we can use it in our definition of derivative. So it'd be square root of 1 minus 3, and instead of x, I will substitute x plus h. And then I will just rewrite that, maybe make it a little bit nicer here. 1 minus 3x minus 3h. I just distributed that negative 3. And so now we can go on with our derivative and substitute everything in and see if we can evaluate this limit. So limit as h approaches 0 of f of x plus h, which we just found, 1 minus 3x minus 3h, minus my original function, which was 1 minus 3x under the square root, all over h. This is going to be equal to my first derivative. All right, so if I thought for a second that I could just substitute in 0 for h, I would do that. If you do, you're going to get 0 over 0, which tells you you have some algebra to do. And I'm hopeful that we remember what the technique is when it looks like this. So I am going to move this equals f prime of x over to the left here, so it's just a little bit easier to work with. I'm not taking it off, I was just relocating it. And then I want to do the technique of rationalizing. I don't know that we've done that enough, so that's why this one's on here too. So when we rationalize, we can rationalize the numerator or the denominator, but it just helps us rewrite it and some factors get moved around. So I'll do the conjugate of the numerator over itself. And what's under the square roots stay the same, those radicands. It's important to note that your numerator and denominator must be the same. I'm multiplying by 1 truly, so I'm not changing the value. I'm just changing the way that this is temporarily going to appear. All right, so I still have limit as h approaches 0. When you multiply out these conjugates, they multiply to be difference of squares. So if you wanted to truly FOIL, as you call it, or distribute, you can. You're going to see that your middle two terms add to 0. So the square root times itself is just the 1 minus 3x minus 3h without the square root. The parentheses will become important in a second. And then the difference of squares, right? Because it's negative times positive, so it turns out to be the difference of squares. And then the other 1 minus 3x times 1 minus 3x under the square roots becomes a whole 1 minus 3x. And maybe now you see the necessity for those parentheses. All over, don't multiply out that messy denominator, just write it down. Don't multiply anything in, don't change anything, just write it down. Okay, if I combine like terms in my numerator, and I'm going to actually distribute the negative 1 sort of up here so that I can see what it's going to become. So here's a look at my numerator. The 1 minus 3x minus 3h stays the same, but then I have a minus 1 and a plus 3x if I distribute that negative. So now when I rewrite it, its limit as h approaches 0 of the 1's add to 0, the 3x's add to 0, and it's just negative 3h is all that's left in my numerator. And I'm going to copy down this denominator. So now I can see h divided by h is 1. You've removed the discontinuity, or the reason that you could not just substitute 0 in from the beginning, so I'm going to go ahead and substitute 0 in now. So I still will have f prime of x. I have no more limit though, because I'm actually evaluating when h is 0, because I've removed that discontinuity, so now I can, or I think I can anyway. So it'll be negative 3, remember that negative 3 is still in my numerator, over square root of, if h is 0, I have 1 minus 3x, and then minus 3h would be minus 0, and plus square root of 1 minus 3x. I don't need to write minus 0, so I'll not look at that. So really, f prime of x is negative 3 in the numerator over 2 of the square roots. Now some people look at this and they look at that previous step and say, oh yeah, the square root times the square root, there's no more square root. It's just itself. Well, you're adding them, right? So be very, very careful. There's a plus in the middle. Okay, so if I have that for my derivative, let's go back to that domain discussion from earlier. So I'm going to copy that down, or actually I think I can see it on my window here. So the same type of conversation is going to occur with domain. Your denominator cannot be 0, and what's underneath the square root, or that radicand, has to be greater than or equal to 0. Well, take a look at where your square root is now. Your square root now is in the denominator. So all I'm going to say is that 1 minus 3x, normally I would say greater than or equal to 0, because I would want to make sure that it's 0 or greater so I can take the square root of it. But I'm actually going to remove that or equal to, because if it is equal to 0, then I'm dividing by 0, and I can't divide by 0. So the only change from my initial function's domain is that now it cannot equal. So I would say the domain of f prime of x is negative infinity to 1/3 with a parenthesis. So that's the only change to that domain. Okay, I hope you found this video on derivatives helpful, where we did a little bit of algebra, or quite a bit of algebra at the end, and looked at some of the graphs throughout the video. That might be a skill that you want to practice more and keep describing to yourself and writing down why those derivative graphs are what they are. Thanks for watching.